Hi everyone, I am Chen Hao and today I'll be covering the topic of the spin tree group as well as the related Lie groups SP1, SU2 and SO3. This content will be from the book Quantum Theory, Groups and Representations by Peter Voigt. Everything I present here is not original content and can be found in chapter 6.2.3 on rotations and spin groups in 3 dimensions. The reason for this walkthrough was because I found it difficult to understand this chapter and could not find much video resources on this topic. Link to other resources will be found in the description. Hopefully, you'll find this informative and useful. If there are any questions, feel free to drop me an email or drop a comment. If there are any errors, please notify me as well, and I will be mentioning the erratas in the video description. So please check the video description before continuing with this video. As a disclaimer, I am not an expert in this topic, so please do not take my word as pure fact. I will most likely have a mistake in this presentation, but nonetheless, I hope you find this video useful in understanding the spin tree group. Let's begin. Here's an overview of the spin tree group. I will present parts of the book in this set of slides and explain in further detail each page of the book. In summary, the SU2 Lie group is isomorphic to the SP1 Lie group, and because SU2 and SP1 is a double cover of SO3, we identify it as the spin tree group. We explore different representations of SU2 and SP1, and in so doing, find out that it behaves similar to that of SO3. We will then look at the Lie algebras of the Lie groups and find out that they are isomorphic to one another. Here are some prerequisites. I recommend Nakahara for Lie groups and manifolds, and Brian Hall chapter 4.2 for the adjoint representation. You can check out Wikipedia as well. I will also assume you have a basic understanding of representation theory and quaternions. This can be found in the chapters prior to this chapter in Peter Voigt's book. Here are some basic definitions made in the Peter Voigt's book. We'll mention them briefly. The SP1 group is the non-commutative group of unit-length quaternions. The SU2 group is the group of 2x2 complex matrices which are unitary. The SO3 group is the group of orthogonal 3x3 matrices. And by definition, the spin tree group is the double cover of SO3. You should be familiar with the ideas of Lie algebras as well. One way to define it is that the Lie algebra is the tangent space at the identity element of the Lie group. The adjoint representation is the representation of G on its Lie algebra. It can be computed by taking the differential of the conjugation map defined on the Lie group G. Remember that it makes sense as a representation because the Lie algebra itself is a vector space. If you want to find out more information about the adjoint representation, please check out Wikipedia or Brian Hall's book. Here's the base picture we have in mind. We have the Lie groups here and the Lie algebras here. By definition, spin tree is a double cover of SO3. Here, the corresponding Lie algebras and their basis vectors, which satisfy the commutation relation known as the Lie bracket. Also keep in mind that the vector properties are present in the Lie algebras, meaning that any element in the Lie algebra is a linear combination of the generators, aka the basis vectors. Without further ado, let's start on the book. The author first begins by defining the conjugation action on the quaternions. Here, Q and U are elements of the quaternion set. We define the action of U on Q to be U times Q times the inverse of U. We then realize that if we expand Q out in its real and imaginary components, the imaginary being the ijk components, the real part doesn't get altered by the conjugation action. This motivates us to let U be a purely imaginary quaternion, as seen over here, V arrow, denoted by V arrow over here. We can then redefine U to be an element of SP1. So what we have here is an action of SP1 on the purely imaginary quaternions. It is worth noting now that the space of purely imaginary quaternions is actually the Lie group, the Lie algebra of SP1. This definition here is secretly the adjoint representation of the Lie group SP1. The purely imaginary quaternions can be identified with the space R3 simply with this mapping over here by mapping the components. And because this conjugation action doesn't change the length of the purely imaginary quaternion, as seen here, we can think of the imaginary quaternion as an element of R3. Then the SP1 corresponds, the element of SP1 corresponds to SO3, where SO3 is a group of transformations that maintain the length of the vector. Specifically, if we define a map from SP1 to SO3, and this can be quickly checked to be a homomorphism, and we'll see a more explicit construction of this map later. It is interesting to note that two elements, U and minus U of SP1, both map to the same rotation element in SO3. One can show that this homomorphism is surjective, and it is known as the covering map. Specifically, it is a twofold cover. This makes SP1 a double cover of SO3. And because we defined spin 3 to be the double cover of SO3, spin 3 then equals to SP1. With this, we have established the relationship between SP1 and SO3, namely that it is a double cover. The homomorphism from SP1 to SO3 can be thought of as a R3 representation, or rather the adjoint representation, where for the adjoint representation, SP1 acts on the space of purely imaginary quaternions, and for the R3 representation, SO3 acts on the 3 vector. It is interesting to note here that the defining representation of SO3 is the R3 representation, and the adjoint representation of SP1 is the representation where the vector space that SP1 acts on is the Lie algebra of SP1. It is because the Lie algebra of SP1, which is a space of purely imaginary quaternions, can be identified with R3, namely the components of ijk with the 3 tuple, that every element of SP1 can then be easily mapped to an element of SO3. With our diagram, we have filled up a bit more over here. Topologically, SP1 is not a trivial cover, meaning that SP1 cannot be expressed as a Cartesian product. We refer to this photo here. Now we investigate the Lie algebras of SP1 and SO3. Now the book presents this in a certain manner, but I understood it almost going in a reverse manner. So I'll present my understanding of this section, but feel free to read the book as well. The equations here are identical anyway, so there shouldn't be any ambiguity. Now, for my understanding, every element of SP1 may be parameterized by theta, W1, W2, and W3, corresponding to the real and imaginary components of the quaternion. According to this equation here, we have the condition that W1 squared plus W2 squared plus W3 squared must be 1. If we express this as W arrow, where W arrow is following this definition here, then we can write this in a more compact form. We can then Taylor expand by noting that W arrow squared is minus 1, as seen here. We can Taylor expand the exponential function, and we will find that it is of this form. So we can write any element of SP1 as an exponential of the Lie algebra. So noting, if we define this to be a curve in SP1, where the parameters of the curve is theta and W, and varying theta, we will get a curve, one parameter subgroup of SP1. If we note that theta equals 0 would give the identity element in SP1, then we can define the velocity vector at the identity element by taking the derivative of the parameterized curve, parameterized by theta, and evaluating at theta equals 0, which is the identity element. This would then give us the velocity vector at the identity element of the SP1 group. And evaluating this derivative of a quaternion here, we just get the W arrow, which is the space of purely imaginary quaternions. We can then say that the Lie algebra of SP1, which is the tangent space at the identity element, is hence the space of purely imaginary quaternions. Now remember the fact from the first slide. Remember from the first slide that we said that the action of SP1 on the space of purely imaginary quaternions is the adjoint representation. Well, this makes sense now because we have evaluated the Lie algebra of SP1 to be the space of purely imaginary quaternions. And this action here, the conjugation action here, is hence obviously the adjoint representation, where V arrow is the element of the Lie algebra and U is an element of the SP1 group. Now we return back to the text. And the next thing we try to do is explicitly evaluate the homomorphism we have constructed. We try to find an explicit expression that maps SP1 to SO3. This can be done now because we have an explicit equation for an element of SP1. Namely, we have the U of theta and W is the exponential of theta times W arrow. Here, the author has presented a construction of the homomorphism, and the author then proceeds to prove it. The proof is a tedious calculation, but it's relatively straightforward, so I will not cover it. However, I wish to reaffirm a concept here. We know that there is a way for SP1, the Lie group, SP1 to act on its Lie algebra SP1. Namely, the action of U from SP1 acting on a purely imaginary quaternion V arrow is defined by the adjoint representation. This action is the conjugation of quaternions. If we evaluate this, we can see that it gives us another purely imaginary quaternion. If, however, on the other hand, we see that SO3 can act on R3. R3 is the vector space, and this is known as the defining representation of SO3. An element R of SO3 acts on the 3 vector V bolded by matrix multiplication with the vector. We then see that the corresponding element we get in R3 looks a lot like that of the Lie algebra SP1. We see the correspondence between the adjoint representation of SP1 and the defining representation of SO3. Because U theta W and R2 theta W acts on V arrow and V bolded in a very similar fashion, if we identify V arrow with the bolded V, we have the explicitly constructed a map from SP1 to SO3, given by this, or over here as well. If you're confused by this part, please refer to the helpful definitions up here. Namely, it is important to note that V arrow, the one with the arrow up here, is an element of the set of quaternions with the extra condition that it is purely imaginary. It's IJK only. This then makes it possible for the quaternion in SP1 to act on V arrow, which is also a quaternion, by quaternion multiplication. On the other hand, V bolded over here is a tuple of 3 real numbers and is hence an element of the vector space R3. Therefore, it makes sense for an element of SO3, which is a 3 by 3 matrix, to act on an element of R3, which is the bolded V over here, by matrix multiplication, because it's a 3 by 3 matrix acting on a 1 by 3 vector. Realize that if we confused V arrow here with the V bolded, then it seems like it wouldn't make sense for the quaternion to act on a 3 tuple of real numbers. Hence, understanding this difference between W arrow or a V arrow and bolded V is important in our understanding of the adjoint representation action and the defining representation action. As such, we have explicitly evaluated the homomorphism that takes SP1 to SO3. As such, we can add something to our mind map here, which is the explicit construction of the homomorphism mapping. We then investigate the Lie algebras of SP1 and SO3, and we find that they are identical. How so? Well, given the homomorphism from SP1, Lie group SP1 to Lie group SO3, we may obtain the Lie algebra homomorphism, which is really just the push forward of the homomorphism for the group. This Lie algebra homomorphism isn't too hard to calculate, and the author does so over here by calculating the derivative of the matrix. We can obtain the Lie algebra homomorphism for the basis vectors I, j, and k to find that it maps to the basis vectors of Lie algebra SO3. This identification of basis vectors from SP1 to SO3 would then give us an isomorphism between the Lie algebras SP1 and the Lie algebra SO3. Now that we are done establishing the relationship between the Lie group SP1 and the Lie group SO3 and their corresponding Lie algebras, we move on to SU2. We can find the isomorphism between the Lie group SP1 and Lie group SU2 by mapping any quaternion to the following matrix. This matrix can be expressed more obviously in the Pauli matrices. And the mapping from the quaternion to the 2x2 matrices is given in terms of the basis vectors over here. Sorry, I mean not basis vectors, in terms of the components. Then taking the determinant of this matrix, as seen over here, we can see that it corresponds to the length of the quaternion. And we know that any quaternion of unit length 1, which is an element of SP1, will map to a 2x2 complex matrix with determinant 1, meaning that any element of SP1 under this transformation rule between the quaternions and the 2x2 matrices, any element of SP1 will map to an element of SU2. This then gives an isomorphism between SP1 and SU2. Now we proceed to show that this is an isomorphism of Lie algebras as well. The Lie algebra SP1 is the set of quaternions with Q0 equals to 0. In other words, the Lie algebra is a set of purely imaginary quaternions. And this corresponds to elements of the Lie algebra of SU2 because the SU2 Lie algebra only has the Pauli matrices as the basis. There's no identity matrix here that is part of the basis vectors. So we can see that Q0 equals to 0 neatly maps elements of the Lie algebra SP1 to the elements of the Lie algebra SU2. One may check the commutation relations for the Lie algebra SU2 as seen over here, as well as that for the SO3, Lie algebra SO3. As such, we found out that the Lie algebras SP1, SU2, and SO3 are isomorphic to one another, as there is a one-to-one mapping for each of the generator of the Lie algebras. This first one being the SP1 Lie algebra, the second one being the SU2 Lie algebra, and the third one being the SO3 Lie algebra. Hence, we have completed our diagram for the Lie algebras. One may be interested in constructing the explicit mapping from Lie group SU2 to Lie group SO3 as well. This may be done by first finding out what each element of the Lie group SU2 looks like. We find this is possible via exponentiation of the Lie algebras. We then evaluate the adjoint representation for SU2, which is the action of the Lie group SU2 on the Lie algebra SU2 via conjugation, as seen over here. This can be identified with a transformation of the R3 vector by the Lie group element SO3. In other words, reiterating, when an element of SU2 acts on an element of the Lie algebra SU2 via this conjugation action as defined by the adjoint representation, it corresponds to a rotation of the tree vector defined on the vector space R3. It corresponds to that rotation of that vector with by the element of SO3. More notably, we can note that minus omega and omega will map to the same R, meaning that once again SU2 is a double cover of SO3. Actually, this comes as no surprise because previously we have established that SP1 is isomorphic to SU2. And hence it makes sense that the properties of the Lie group SP1, i.e. the adjoint representation and the double cover, will be the same as that of Lie group SU2. We may therefore fill in our diagram with the adjoint representation of SU2 corresponding to the defining representation of SO3. Now lastly, the author provides an explicit mapping which does not give us much insight except maybe for the fact that the negative of this matrix will end up with the same SO3 matrix, once again establishing that minus omega and omega of SU2 will map to the same element in SO3, and hence finding out that SU2 is the double cover of SO3. So here is a summary, which I will just thoroughly read from the book. Firstly, spin tree is topologically the same as S tree, although this is not the focus today. We have two explicit constructions of the spin tree group, namely the Lie group SP1 and the Lie group SU2. We have showed that these two groups, SP1 and SU2, are isomorphic to one another, to each other, by identifying the IJK components with the Pauli matrices. Next, SO3 has a Lie algebra that is isomorphic to SP1 Lie algebra and the Lie algebra of SU2. Next, we can then derive the Lie algebra isomorphisms from the group representations via differentiation. And we have seen that two representations of various groups. The first being the defining representation of SO3, which is the representation of the SO3 on the vector space R3. This can be identified as the adjoint representation of SP1 or SU2 as well. This is known as the spin 1 representations, the reason of which will be clear when we investigate the irreducible representations of SU2. Lastly, this one we did not cover. The defining representation of SU2 is not a representation of SO3. What we investigated in this video was the adjoint representation of SU2. So the last one is not of great relevance to this video. I hope that you have found these slides informative and educational. I might be reposting this video if I get any feedback, and I definitely learned a lot while creating this set of slides. Thank you.